So let's do a quick review of what you guys did yesterday. So the term unique means one of a kind. So we have one S and we have two CLs. Well, since we have one S is going in the center. That means the CLs are going around it. We want to add up all of the electrons available. There's 6 there and 14 here for a total of 20. I got that from the periodic table. Cl, 7 each, and sulfur, 6. So if we take a look, that's 20. Here we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We want to make sure that every single thing has a set of 8 around it, because that is what we call the octet rule. Once we fulfill that, then it's actually a stable electron configuration. Here we have SiCl4. So we have Si in the middle. So we have Cl, 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 and Cl. There's 4 Cl's around it. Si is 4 plus 4 times 7, which is 28, plus 4 is 32. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. NBr3, NBr3. So if we take a look, N is unique. Br, Br, Br. N is in group 5A. Br is in group 7A. So that's 21 plus 5. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And 5 plus 21 is 26. 24, 26. CBr2Cl2. C is unique. Br, Br, Cl, Cl. Now, if you had Cl and Cl and Br, that's okay. Because when we look at something, for example, my hand, when we look at it, it's the same hand, but we can look at it from different angles. So if we take a look, 2, 4, 6, actually I need to count them up first. 4 plus 14 plus 14, that's 28 plus 4 is 32. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So there are those 4. Let's make them real quick. So let's look at these shapes. So each of these sticks is going to represent 2 electrons. A stick that is between 2 of these spheres represents a bond. A stick that is by itself represents a lone pair. So if we take a look, here is S, and here is Cl, and here is Cl. So this is SCl2. If we take a look at it, on my paper, it looks like a straight line. That's because we're looking at it from this angle, right? In reality, it looks like this from the side view. This is what we call the valence shell electron pair repulsion theory, or VSEPR for short. Valence shell, so basically outer energy electrons, pairs, because everything's in a pair, repulsion, because they're all pushing against each other. If we take a look around this sphere, about 109 is the angles that each one of these can be away from each other the most. If we were to take a look at this guy right here, let's go ahead and put on 2 more CLs. So when we look at it there, we're looking at it at this angle. right? But in reality, it looks like this from the side and stuff. It's the same shape as D right here. Let's look at NBr3. We're going to take away one of those atoms because we only have 3 Br and N. And we're looking at it like from this angle right here. In reality, it looks very similar to the other one. But we're looking at it from this angle where these are flat straight across and this guy is downward. Now, let's go to the back of this page, or actually the back of the packet, to this page right here. So it says central bonded atoms. That's how many atoms are bonded onto the central atom. Lone pairs. This is how many lone pairs there are on the central atom. Now, for the quiz next week, all we need to know is down to here. You'll be able to use this because I can't stop you. Usually would have you memorize this. We're going to mark out 119 here, so you can cross that out. And we're going to keep the 104.5 here, so you can mark out the 109.5 on Angular. So let's take a look. If we're looking at sulfur here, we have 1 bonded atom, 2 bonded atoms. This and this, these 2 things are lone pairs. So sulfur here has 2 bonded atoms and 2 lone pairs. So if we look back on the back here, we go down here to number of central bonded atoms. Here's 2 and 0 lone pairs. That's not the shape we're looking for. Here's 2 and 1 lone pair. That's not the shape we're looking for. Here's 2 bonded atoms and 2 lone pairs. So the actual electron domain for that is tetrahedral, but the shape I'm looking for is angular. So if we take a look for the shape for this one, we're going to put angular. And what does angular look like? Angular looks like this. This is the angular. Now the angle here, if you're in geometry, that angle is written on that page at the end, is 104.5 degrees. Now what causes that is these electrons up here. It's pushing these atoms down toward each other, making that angle what it is, 104.5. So let's do this one. I'll give you a second. If you want to type in the chat, you can. We have 1, 2, 3, 4 bonded atoms and 0 unshared pairs. I want the shape and the angle. 4 bonded atoms and 0 unshared pairs, 0 lone pairs. I'm going to drink while you look at that one. On the back of that, you may want to pull that page off. Very good. It's been said in the classroom that the shape is tetrahedral, which is correct, and the angle is 109.5. What was done here was we knew it was 4 bonded atoms Keep pulling that thing the wrong way. So we go down here. We found 4 bonded atoms, 0 unshared pairs. That is tetrahedral. That is 109.5. The way that looks is this right here. Boom, boom. So all of these are tetrahedral because each time all we're doing is we're pulling one of these atoms off and replacing it with a lone pair. So this is what we would call shape-wise trigonal planar. The domains are still in a tetrahedral arrangement. And then if we pull another atom off, we've got angular. The arrangement is still tetrahedral. So let's do the other two. Count them up. 1, 2, 3 bonded atoms and 1 unshared pair. Somebody want to type into the chat what 3 bonded atoms and 1 unshared pair would be? Type it into the chat. Or you can unmute yourself. So controversial though. What is the shape? 3 bonded atoms, 1 unshared pair. Landon, what do you think? You do? Yeah. Let's give Ka a chance. Ka, what is it?
Man, what happened, bro? Like, I just came back in my room.
What you been doing? You get some Fruit Loops?
No, I want to get some water.
Oh. Like just regular water? Like from the toilet?
No. But what's the problem? My bad, though.
What is the problem? We are trying to find out the shape of something that has 3 bonded atoms and 1 lone pair.
Two particle atom. Would it be CI?
Well, we only have so many right now. We only have down to here, so it won't be seesaw.
Yeah, I'm looking at my chart right now.
So we're looking for a 3
Failure or angular?
1 in this column. So you're looking for a 3 in this column and a 1 in this column, right?
Would it be a triangular pyramid?
Close. Trigonal pyramidal.
A trigonal pyramid.
Trigonal pyramidal or trigonal pyramidal. Yep. So that's trigonal planar or pyramidal. Trigonal pyramidal. One more. Sydney Castiamani, somebody else. How many bonded atoms are there on this central one? Good job. They know it here. Nothing typed into the chat. You guys are getting oof. People are emailing me about extra credit, but we can't count the number of bonded atoms here. Whew. You guys are making me work hard. There we go. Chat is open now. There we go. 4. All you got to do is count the number of atoms bonded to the central one. 1, 2, 3, 4, right? So then we go over here. There are 0 lone pairs. So we are looking down this column for a 4 and this column for a 0. Sydney, type in what the shape should be. Yeah, you corrected yourself. What should it be? You're looking for a 4 in this column and a 0 in this column.
Does it like start with a T? I can't really read it.
It does start
Like-
with a T. Do you not have a copy of this?
Let me pull it up. Hold on.
How's that? Starts with a T.
Tetrahedral.
Tetrahedral. Yep. Tetrahedral. Tetrahedron is a four-sided thing. Tetrahedral is the shape of these atoms. All right. Good, good. Let's take a look. Let's take a look at our next exercise. So let's pull back a little bit. We want to pull back to the part where it says multiple bonding. So page 6, please. I'm going to grab attendance real quick. So I got Amani, Brianna's in here, right? Cassidy, Ka, Landon, Lanaya. Is Michaela out there in the world? No Michaela.
What do you just want to do?
Well, what?
Oh, my bad. My bad.
Gooch. No Gooch, no Michaela. All right. Cool, cool. All right, so I want you to open up to page 6, Ka. You there? You on page
Yeah, I'm
six?
there. I'm there.
All right. You on page 6?
Yeah, I'm on page 6.
All right, cool. I'm gonna open it up so these guys can see a little better here. All right, multiple bonding. So what happens when the number of electrons that you counted are not the same as the number from the periodic table? Most of the time, an atom is bonded to another atom with a single pair or sharing one pair. This is known as a single bond. Sometimes an atom must share 2 or even 3 pairs of electrons to satisfy the octet rule. This is called a double bond or a triple bond if it's sharing 3 pairs of electrons. Remember, every line means 2 electrons, and they are done in pairs. You'll know that the Lewis structure needs double or triple bonds if you run out of electrons. So let's do one. We have oxygen. Last semester, if your teacher was good, they taught you that oxygen was diatomic, meaning that it exists as O2. So if we have O2, each oxygen has 6 valence electrons by looking at its group number. Oxygen, 6A. 6 times 2 equals 12 electrons available to use. Here are 2, 4, 6, 8, 10, 12, 14. That's giving everything the octet. The problem is what number did I say whenever I added all these up? 2, 4, 6, 8, 12. I'm sorry, 2, 4, 6, 8, 10, 12, 14. I'm showing 14 electrons, but 6 times 2 is 12. That means I am 2 over my electron budget. Right? I'm 2 over my electron budget. So what must I do? Well, that means I need to form a double bond. By saying that these 2 atoms are sharing another pair of electrons, that means I can get rid of 2 of these electrons. Just watch what happens. If I take and make a double bond here, right? So if there's 2 lines between them, I can take a pair of electrons from this one and this one. Because now I have 2, 4, 6, 8 and 2, 4, 6, 8. Right? But if we count these up, 2, 4, 6, 8, 10, 12. So after I take away 1 from each, I am back down by 2 because I put 1 here and I took 1 from there and there. That gives me 2, 4, 6, 8, 10, 12 electrons. So now that's good. Well, let's try nitrogen, because if your teacher was good, they taught you that nitrogen is also diatomic. How many electrons total will I get from nitrogen when I add them up from the periodic table? Find nitrogen on the periodic table, find its valence electron number, and we have 2 nitrogens. N2, how many total electrons are available for N2? Ten, right? We go here, we find 5A, right? Yeah, that's lagging pretty badly. 5A for nitrogen, so it's a total of 10 electrons. So here we have 2, 4, 6, 8, right? 2, 4, 6, 8. Now the problem is if we add all these up, 2, 4, 6, 8, 10, 12, 14, 14. We end up with 14 total. Right? We're how many over our 10? 4 over our 10. That means we're 2 pairs over our 10. So that means we need 2 more bonds put in. Anytime we put a double bond in here, we get rid of 1 pair from each of those. Notice what that does. 2, 4, 6, 8, 10, 12 now. Right? We're still 2 over. We're still 2 electrons over. So what we're going to do is we're going to put another bond in. And anytime we do that, we take away 1 pair from each one we put the bond between. So now if we count these up, 2, 4, 6, 8, 10, we're perfect. We have the perfect number of electrons like we should. All right, CO2, who's in the center? Who's unique? CO2, who is unique? Carbon, good. Try this one on your own. Count up the total number of electrons. It does have multiple bonds, so you're gonna have to deal with that. I'll give you about 3 minutes to do that one. Now, there's 2 possible outcomes that students can come up with for this. This is not one. Why is this not possible? Well, we have 4 plus 12, which is 16, right? 4 plus 12, which is 16. We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So we have 4 extra electrons than we should. How many bonds does that mean we need to make extra here? If we're 4 electrons over our budget, we need to make another bond for each 2 we're over the budget. So how many more bonds do we need to make? 2 was said in class. Hopefully you agree at home. There's 2 options. Remember, anytime we do this, we put a double bond in there. We need to take away 1 from each one that we bonded the second time. Now, the reason we do that is it takes us down by 2. 2, 4, 6, 8, 2, 4, 6, 8. So both of these are now fulfilling the octet rule. But we'll look at the overall number. 2, 4, 6, 8, 10, 12, 14, 16, 18. Right? Count those up. Now we're only 2 over. So we need to make another bond somewhere. This is where it differs. One option we could go, okay, well, we know triple bonds exist, right? We just did one with nitrogen. So if we put a triple bond there, boom, boom. And here's the thing, that is unlikely. Here's where we were. How about you? What you thought? Yeah, very good. So this is one option. And as I said, this one does not exist. The other option is we double bond it to the other oxygen. Right? This is actually what's more likely to exist. Nature tends to do something we call symmetry. This is symmetrical. This is not, right? This symmetrical one right here, symmetrical, not symmetrical. This one is the good one. This one is not. Last thing for today. What if you have more than one unique atom? You have what's known as unique atom conflict. So how do you know which atom goes in the center? Well, it's going to be the one that forms the most bonds. So I call this how do we do this? What do I call it? Oh, I know what I call it. Doesn't start with C. I call it honk. Hydrogen and halogens tend to form 1 bond, oxygen forms 2, nitrogen forms 3, carbon normally forms 4 bonds. So if you have carbon available, it's in the center. If you have nitrogen available and no carbon available, nitrogen's in the center. If you have oxygen available, but none of the other ones, oxygen is in the center. Otherwise, you go with unique. So for example, H2CO, both C and O are unique. C can form more bonds. So I'm going to put C in the middle. Right? So we have 2 electrons from hydrogen, 4 from carbon, and 6 from oxygen. That's a total of 12 electrons total. Currently showing 2, 4, 6, 2, 4, 6, 8, 10, 12, 14. Remember, everything has to get 8 except for hydrogen. So I just said I'm showing 14. Well, here's another cool little thing. We know carbon likes to form 4 bonds and oxygen likes to form 2 bonds. I'm 2 electrons over. my limit. So what does that mean? I'm gonna need a multiple bond here. Who's it going between? Carbon likes 4 bonds, oxygen likes 2 bonds. Carbon currently only has 3 and oxygen only has 1. So we're gonna double bond them up. There we go. How about NOF? NOF, NOF. Who's in the center? Remember honk. 1 bond, 2 bond, 3 bond, 4 bond. Nitrogen, good. This was said in class. So there's our basic setup. We have 5 plus 6 plus 7. That's 12 plus 6, which is 18. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I am 2 over my 18, so I need a what? I need another bond. Who's it going between? Nitrogen and fluorine or nitrogen and oxygen? Think of honk. How many bonds does oxygen like? Yeah, 2, right? Because oxygen likes 2. We're going between nitrogen and oxygen. Boom. There we have it. Dun, 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 dun. So what I would like for you to do is problem 2 and problem 4. Problem 2 and problem 4 for tomorrow. You have the rest of the class to do it? Problem 2 and problem 4. If you have any questions, by all means, stay after. Otherwise,